So this section is on the giant planets. So the giant planets are Jupiter, Saturn, Uranus, and Neptune. There are 4 of them. These are their approximate sizes. You can see Jupiter on the left is a little bit bigger than Saturn, and they're both considerably larger than Uranus and Neptune that are about the same size. There's some striking similarities here between the 2 on the left and the 2 on the right. Often the 4 giant planets, which are called Jovians, or giant planets, are divided into 2 groups. Uranus and Saturn are called gas giants, and Uranus and Neptune are called ice giants sometimes. The brown color that you see in Jupiter and Saturn seems to come from ammonia ice particles in its atmosphere, and the blue in Uranus and Neptune seems to come from methane ice. Here's some planet data. Jupiter is about 5 astronomical units from the Sun. That's about 5 times Earth's distance, right? Saturn's about 10, Uranus is about 20, and Neptune's about 30. Their periods, this is how long it takes them to go around the Sun one time. Jupiter is 12, Saturn's about 30, Uranus is about 84, and Neptune's about 160. So that's 164 years, Earth years, for Neptune to go around one time. The diameter of these in kilometers, we've talked a little bit about. So these are, in kilometers, the Earth is about 12,000 kilometers. And so Jupiter is more than 10, but Jupiter's about 11 Earth diameters. Saturn's about 10. And then Uranus and Neptune are about 4 or 5, something like that. If you want to compare their masses, Jupiter is about 318 Earth masses. Saturn is about 100. So Jupiter is about 3 times the mass of Saturn, even though it doesn't look a lot bigger. We'll get to that. Uranus and Neptune are about 14 and 17, so roughly 15 on average between the 2 of them. The density of these planets, these are much more consistent with the density of water, which is 1.0, than they are of rock or metal, which is, the density of the Earth by comparison is about 5.5 grams per cubic centimeter. And these guys are much closer to 1. And so that's why terms like ice giant and stuff come up. Notice that Saturn is the least dense of them all. Saturn is less dense on average than water. And so if you could fit it in your bathtub, it would float. Another interesting thing about the gas giants is that the Jovians, the giant planets, gas giants and the ice giants, is their high rotational speed. So even though Jupiter is 11 times Earth's diameter, it rotates actually faster than the Earth does. It goes around in just under 10 hours. Saturn does a full turn in just under 11 hours, and Uranus and Neptune are about 17 hours. They've got a much shorter day, even though they're much bigger, so their surface is spinning really fast. The rate of speed of their surface is like 20 times what the Earth's is. So, fast spinning. So these are missions that have been sent that have at least gone past the Jovian planets. And so there's been a lot. Jupiter's the closest one, so there's been a lot that's gone by Jupiter. Our first ones were in the 1970s. We had 4 missions in the 70s, none in the 80s, but we had 2 in the 90s. Notice these are called flybys. And then the first orbiter we sent to Jupiter was the Galileo orbiter in 1995. That's already almost 30 years ago, but it was a spectacular one. Many of the cool images we have of Jupiter are from Galileo. The Cassini probe was a flyby because it was an orbiter for Saturn. Later, the New Horizons mission, which went to Pluto and beyond, also did a flyby. And then there was another orbiter in 2016 called Juno, which was doing a north to south orbit, examining the poles of Jupiter. Saturn's also had a few flybys, the Pioneer and the Voyager probes. We'll talk more about them as we go, but they're actually both still sending back data. They were launched in 1977. The Cassini probe was the first orbiter and only orbiter for Saturn, I believe, and it was put out of commission a while ago, but it was there for a long time, like, I don't know, 8 or 10 years or something like that. And all the cool images we have of Saturn really come from the Cassini probe. And finally, just a couple. Voyager 2 has been to Uranus and Neptune, both in the 1980s. Both flybys. So let's just talk for a minute about these missions. They're kind of interesting. If you want to go explore a planet, the cheapest thing to do is do a flyby. So if you do a flyby, you're just shooting something out there, kind of letting it get caught in that planet's gravity, and it just zings on past it. That's the easiest thing to do, and so it doesn't give you a lot of time to look, because you're generally going pretty fast when you go by. But we did a nice tour of the solar system with the Voyager probes and the Pioneers in the 1970s. The next most sophisticated thing you can do is an orbiter. This is a spacecraft that's put into orbit around the planet or moon or whatever it is you want to look at. So the reason this is hard is because you actually have to have fuel to slow yourself down. If you don't have fuel to slow yourself down, you'll just shoot on past. You'll speed up as you go in, and you'll roll on by. And so bringing fuel enough to bring an aircraft to a stop, a spacecraft to a stop, is very challenging, because it adds a whole lot of weight, and then that weight has to be lifted by additional fuel in the launching rocket. And so even just adding some fuel is very expensive. So an orbiter is a lot more challenging to do than a flyby. They've started doing some sophisticated things to slow the orbiters down without using a lot of fuel. And one thing they do is skim through the atmosphere. So if you want to go to Mars, you can put yourself in a trajectory that skims through the atmosphere and slows you down. And then you can use the gravity from the planet to pull you back around again and skim through the atmosphere again. And then you can do that several times to slow yourself down and finally put yourself into an orbit. But those require some fuel also to realign the orbit as you go through, to realign the trajectory as you go through. And so anyway, the orbiters are much more challenging than flybys. Obviously, landers are even more challenging. We put lots of landers on Mars. And not only do you have to stop, but then you have to successfully drop something onto the planet with parachutes or fuel or something. And those are extremely challenging. But NASA's been quite successful at putting rovers, for example, on Mars. I forget how many we've had on Mars, 6 or 8 or something like that. Quite a few. But really, really challenging. And even more sophisticated than that is then a return mission, where you're going to land on a planet and then collect something and then send it back to Earth. And these are just robotic spacecraft, so we're not even talking about transporting humans yet. But all of these are very increasingly sophisticated. So flyby, orbiter, lander, and return mission. And so it'd be nice to be able to do something more sophisticated to the outer planets than what we've done already. Just for the sake of discussion, let's talk about the Voyager 2, for example. It launched in August of 1977, and took it 2 years to get to Jupiter, and then 2 more years to get to Saturn, and then 4 years to get to Uranus, and then 3 more years after that to get to Neptune. And so it got to Neptune 12 years after it was launched. That's 12 years of flying through the sky. What's amazing about them is that obviously they had no technical problems, or no serious technical problems, because you can't send somebody up to fix them. In fact, Voyager 1, which kind of went perpendicular to the direction of the solar system, to the plane of the solar system, and Voyager 2, which stayed in the plane, are both now 45 years later still sending back data. They're getting sketchier, but it's a real tribute to the people who built it that after all these years they're still sending back data. Oops. So a little bit about these spacecraft. If you want to send a spacecraft out to the Jovians, how are you going to power it? And so fuel is expensive to carry. It's very heavy if you just want to put rocket fuel in there, like gasoline in your gas tank. And so usually they want electrical power of some kind. And so one way to do that is with solar panels. And that works for the inner planets, the terrestrial planets, Mercury, Venus, Earth, Mars. But these outer planets, sunlight at Jupiter is 25 times dimmer than it is where the Earth is. It's about 100 times dimmer where Saturn is, 400 times dimmer where Uranus is, and 900 times dimmer where Neptune is. It's impractical to think you can use solar panels to power anything or even to recharge batteries because the power at that distance is so low. And so what we do is we use nuclear power to power these spacecraft. And the Voyager probes, for example, have been running on nuclear power for 45 years, and they're still going reasonably strong. There are some challenges with that. Obviously, you don't want to have a launch failure because then you scatter nuclear waste around the country, around the world, around the globe somewhere. But it's really, as far as we know now, the only really practical way to produce power at great distances from the sun. So here's a thermometer. I don't know if you can even see this, but this is the temperature of the planets. You see Venus is the hottest, and then next to Venus, let me just see if I can read off these temperatures. I've got them in a table later. Venus is about 860 degrees Fahrenheit. These are sort of average temperatures at the surface. I know it says giant planets at the top, and we'll get to those in a second. Mercury is 323, Earth is 59, Mars is minus 85. So these are sort of average surface temperatures. It doesn't make much sense to talk about the average surface temperature for like Mercury, where the difference between the daytime and nighttime temperature is so giant. You're averaging, the number you're getting is in the middle of two numbers that are very extreme. But for the Jovian planets, these numbers are actually pretty sensible because there isn't a lot of difference between the daytime and nighttime temperatures. And so Jupiter's at minus 166 and Saturn's at minus 220. And then Uranus is at minus 320 and Neptune is at minus 330. Notice Jupiter and Saturn are pretty close to each other, and Uranus and Neptune are pretty close to each other. You can see it a little better in this chart. Here are the Jovian planets. Down here, minus 66, minus 220, minus 320, and minus 330. It turns out that both Jupiter and Saturn, and really Neptune also, are like warm light bulbs in space. They both are producing more heat, more than twice as much heat as they're receiving from the sun. Now, we've already said that the sunlight is pretty dim, but they're pretty big planets, and so they're getting a lot of, even though the level of the heat is low, they've got a lot of area, and so they're like an enormous solar panel. Even if the light's pretty dim, you're still going to get some heat overall. But they're producing their own heat from inside. Their interiors are hot or warm, relatively speaking, relative to the space around them. Right? Same thing with Neptune. Neptune also produces more than twice as much heat as it receives from the sun. Uranus is the only Jovian that is cooled off to the point that it's actually producing less heat than it's receiving. So here, the picture A is an artist's depiction of the Galileo probe falling into Jupiter, which it did at the end of its mission. It flew around and took pictures of the moons and all kinds of things, all things Jupiter. And then it launched itself into, kind of ruined itself into Jupiter. because they didn't want, once the spaceship was dead, they didn't want it just flying out there and accidentally crashing into some moon and contaminating it with human matter. So they sent it into Jupiter. Jupiter is, it's very gaseous, and so it would go very deep into Jupiter. It would bury itself in Jupiter. The image on the right is an image taken by the Juno mission, and it's taken from about 100,000 kilometers, which is maybe 60,000 miles or something like that, above the cloud tops. It shows the polar region. All of these little spots you see in here are different types of storms, which we'll talk a little bit about. Jupiter is so gaseous that it's got these hurricane-like things that are in there spinning and doing all sorts of crazy stuff. Here's a picture taken by the Cassini probe when it was at Saturn. And here off in the distance is where you are. If you wave, you can probably see yourself there. That's Earth. It's taken from the Cassini probe at Saturn. This is an image taken by the Hubble Space Telescope of Uranus. Remember, Uranus is on its side as it orbits the Earth, and so as it orbits the Sun. Whereas if you look at Jupiter, we're looking at Jupiter's moon system edge on. Uranus looks more like a bullseye, and so these moons are orbiting around it. By the way, can you guess the theme? Juliet, Portia, Bianca, Puck, Belinda, Rosalind. Can you guess what the theme is for Uranus's moons? The other thing to notice is these pictures were taken, I think they said 90 minutes apart. Look at these little storms going on here, and then look at them 90 minutes later over here. And so you can see that there's some action that was going on Uranus at the time. Uranus is kind of rotating on its side. All the other planets are mostly up and down. I think Saturn is tilted about like the Earth, about 25 degrees, and Mars is also tilted that much. But Uranus is like tilted 98 degrees or something, but close to 90 degrees, so it's almost laying on its side. And if you look at this picture, you sort of get an idea of what happens. So it's rotating like this, and notice that, since the North Pole is always pointing to the right in your picture, 6 months out, not 6 months, half of the cycle, the North Pole is pointed away from the sun, not just tilted like the Earth's is, but pointed completely away. And so Uranus gets very extreme seasons. There's like 6 months where the Uranus Santa doesn't see the sun at all. Not 6 months, half a period. So since the period is 84 years, it'll spend 42 years with no light at the North Pole. And so that creates very extreme seasons. So let's look a little bit at the composition of these planets. Jupiter and Saturn are composed primarily of hydrogen and helium, but hydrogen dominates. But Uranus and Neptune consist in large part of compounds of carbon, nitrogen, and oxygen. So if you look, all of the planets have at their cores ice and rock. That's what the blue and brown are, right? More ice than rock, actually, because the sphere in the center, which is rock, is small compared to the outer shell. That's the ice, and it turns out it means there's a whole lot more ice. It's 5-to-1 or something ice or something like that. And then above that, if you're Jupiter or Saturn, you have this metallic hydrogen, and then above that you have molecular hydrogen. If you're Uranus and Neptune, you just have molecular hydrogen. And so we'll talk about those for a minute and why that happens. So although we cannot see into these planets, astronomers are confident that the interiors of Jupiter and Saturn are composed primarily of hydrogen and helium, despite the fact that they're rocks and ices and those things. Of course, these gases have been measured only in their atmosphere, but calculations first carried out more than 50 years ago show that these two light gases are the only possible materials out of which these planets can be constructed. The outer mantles of Jupiter and Saturn are liquid hydrogen. Its inner mantle is metallic hydrogen. It turns out metallic hydrogen is something that happens to liquid hydrogen when it gets super compressed and it acts like a metal. Hydrogen is normally just a gas, like even on Earth. The Hindenburg had hydrogen gas in it. But if you put it under enough pressure, it becomes a liquid. And if you put it under even more pressure, it becomes a liquid that acts like a metal. And that's what's in Jupiter and Saturn. Let me just pass back up. So these are the metallic hydrogen regions, the red regions, and above that is the molecular hydrogen. Each of these, Uranus and Neptune don't have enough mass to get enough gravity to produce this, to put enough pressure to produce this metallic hydrogen. Unlike the terrestrial planets, the Jovian planets have a density structure with the most dense materials at the center. So it's the densest stuff sinks to the bottom. Also evidence that these guys form the same way the Earth and the other planets did, which is molten. Right. They much larger. They all have much larger portions of ice and rocks, of ices than of rocks and metals. There we go. They all have a much larger portion of ices than of rocks and metals. This is because there's a much greater abundance of ices in the outer solar system. Typical ices, normally we think of ice as just water ice, but an astronomer would say, no, there are lots of different kinds of ice. And some examples are water ice, ammonia ice, methane ice. These are things that normally are liquids or gases to us, but are frozen solids on these planets. And so in the outer solar system, it's very cold, and since there's so much hydrogen laying around that if an oxygen molecule or a nitrogen molecule or a carbon molecule happens to be floating through space, hydrogens will grab it and make the appropriate stable compound. And so if they grab onto if hydrogens see a nitrogen or bump into it, they'll stick to it until they make an NH3. That's a stable one. Or if it's a carbon, they'll make a CH4. Or if it's an oxygen, they'll make an H2O. And so in the outer solar system, there are lots of these molecules. And in the inner solar system, where it's hot, and these are all still gases, they can't contribute to the construction of planets. But in the outer solar system, where these are solids now, they do. And that's why the cores of these planets are ices and rocks and metals, and mostly ices, because there's so much of this stuff laying around. So let's talk about hydrogen and the gas giants. Even in the outer solar system, where it's extremely cold, hydrogen still exists as a molecular gas. And so it is not glomming up and making bigger and bigger particles and turning into planetesimals. The ices that we talked about in the rocks are, but hydrogen isn't, and neither is helium. So hydrogen doesn't clump up. And so in order to capture hydrogen, planets have to capture it gravitationally. I have 3 L's in my gravitationally. I'll fix that. And so what they have to do is they first have to get to be big enough so that they can grab the hydrogen and not have it just escape. Hydrogen gas can escape from Earth and the Moon and most smaller planets unless it's tied up in water or methane or something. But hydrogen gas is light enough they can escape except from very massive stuff. And so what happened in the outer solar system is that there was a lot more stuff to make planets out of, namely all those ices that we just talked about. And so planets could develop very large rocky cores, and eventually they could start capturing hydrogen gravitationally. Since the solar system is about 75% hydrogen by mass, there was plenty available. So once Jupiter, so these planets were forming out of ices and rocks, and once they got large enough, they could grab on to hydrogen. Jupiter was the first to do this, the first to get enough mass. It was close enough in, it was near a lot of material in the inner solar system where material tends to glom up. It reached a large enough size to capture hydrogen gravitationally, and so it got the biggest share. Saturn started later, didn't get its biggest share, and similar with Uranus and Neptune. So Jupiter produces radio waves due to its magnetic field. Jupiter, because of its liquid metallic hydrogen interior, has a very large magnetic field. And if you look, this little region in here is where where Jupiter is. And it's producing a large, complicated magnetic field around it. Different colors are used to indicate the intensity. But you can build an antenna that will listen to radio waves produced by Jupiter's magnetic field. It's not very hard. Jupiter, because it's spinning fast, has a lot of internal energy, and has a huge gravity, produces a lot of storms on its surface. Jupiter's red spot is a famous one. It's approximately Earth-sized. The vibrant colors have to do, they think, with the methane ice. But these are other storms. All these white dots that you see are other storms. The red spot has been around since the time of Galileo. He observed it. And so it's been around a long time. It moves around a little bit and changes color sometimes, but it's been there the whole time. Neptune is seen here as photographed by Voyager 2 in 1989. The blue color is exaggerated with computer processing. But you can see the blue spot, which is a storm on Neptune. So this is a little bit on viewing them. Sometimes you can see Saturn from different angles when you look at it through a telescope. And the reason for that is shown in this picture. It's a little tricky, but the sun's in the middle, and just forget about anything else, and you can just see that Saturn is going around. And just like when the Earth goes around the sun, its tilt remains the same regardless of Saturn's position, right? Now the Earth orbits the sun much closer. That's this little circle in the middle. And so depending on where the Earth is and where Saturn is, we're seeing different things. So if we look at this on the left here, if Earth is here and Saturn is here, we're looking at the underside of Saturn's rings, right? Or if the Earth is here and Saturn is here, we're looking at the top side of Saturn's rings, and so on. If the Earth is here and Saturn is here, we're looking at the rings edge on, right? And so we would see no rings, because as we'll talk, the rings are extremely thin to be seen at that distance. So this is a picture of Saturn as viewed by Earth over a span of 5 years. When Galileo first looked at Saturn, the rings just happened to be edge on. He didn't see any rings at all. It wasn't until a few years later that he saw rings, or a few months later. A little about Saturn's rings. Saturn's rings are 170,000 miles across. That's almost the distance from the Earth to the Moon. And a few hundred feet thick. That's it. A few hundred feet thick. They have some gaps, and that's caused by gravity from some of Saturn's moons. They're composed of icy materials, just like we talked about. Methane ice, water ice, ammonia ice, things like that. They vary from pea-sized to school bus size, typically. Those are the typical range in size. The largest gap in the moon is called Cassini's division. It's named after its discoverer, Giovanni Cassini, which I think we'll mention here in a few minutes. And that gap is caused by the moon Mimas, which looks like the Death Star. So here's a picture of Saturn and some of its moons. Saturn and Jupiter have these bands. They're called belts and zones. They're mostly just the fact that there's different weather at different latitudes, just like we have here on Earth. It just shows up visually on those. So here is the atmospheric structure of the Jovian planets, and you can kind of see that Jupiter has sort of the most compressed atmosphere, you might say, because its gravity is so strong, it squishes it. Saturn's is the least compressed. Uranus and Neptune are in between. There are a few things to notice. Notice that it gets warmer as you go down, and that's because these planets have internal heating in them. It's hard to tell where the bottom of the atmosphere is because there's no surface like there is on a terrestrial planet. So they just talk about what happens as you go in. The cloud tops are appearing at some distance below what we arbitrarily define as zero, a few hundred kilometers below the cloud tops, right? And you can, below the top of the atmosphere. Couple of things to notice. This is ammonia, this blue one at the top, and this is ammonia disulfide, I think, and this is water. I want to ask you to remember the names, but I want you to notice how, like, the temperature for ammonia is about 150 if you go straight down from ammonia. And if you go straight down from ammonia here, it's also about 150. If you go to the water one, it's about 250. If you go to the water one here, that's about 250. So they happen at the same time. They just happen at different depths, these clouds, because that's when the temperature is right for that one to become a cloud, I guess. Ammonia becomes a cloud on Saturn at 250 Kelvin. Similar for Uranus and Neptune. Different gases. These are the winds. So to the right is a wind that's moving in the direction of the rotation. So if it's going to the left of the vertical line, it's moving slower than the rate of rotation. And so it's kind of, if you're staying there, it's kind of going backwards. And notice you can see also the scales on the x-axis are different for each one, right? These wind speeds are very large. 300 meters per second is roughly the speed of sound, so 700 miles an hour. And so at Saturn's equator, the wind is probably 1,000 miles an hour or something like that. Very high-speed winds. A little slower on Neptune, but not a lot slower. The complexity on Jupiter is much more much more significant, right? And it's because it's got all this. It's very compressed because its gravity is so large. It produces a lot of interesting structure in the at different latitudes. These planets are smaller and less dense. They're not being subject to the same stress as the atmosphere in Jupiter is. The other thing is Jupiter is, of course, a lot closer to the sun than these guys are, so it's getting a lot more external heat, and it produces more internal heat. All of those factors tend to affect the severity of the weather on the planet. On Earth, we get much more variation in our weather for different latitudes than you would see here on Uranus and Neptune. These are some questions. Be sure to check the PDF version because I'll probably add some to that.